Model predictive control with visibility graphs for humanoid. Path planning and tracking against adversarial opponents. Figure on the right illustrates the path planning and tracking process. Given an initial and final pose, the path planner finds the optimal path while avoiding obstacles using a modified version of visibility graphs called Dynamic Augmented Visibility Graphs, DAVG. Linear interpolation is then used to generate a trajectory with time stamps. Finally, a modified version of MPC called Collision-Free MPC, CFMPC, is used to generate a collision-free control signal while also considering the dynamics of the robot. We make the visibility graph computational efficient by selecting necessary obstacles using active region. Besides, for humanoid robots, turning is time-consuming. Therefore, our visibility graph takes the turning angle into consideration by augmenting the states. Trajectory tracking, the robot might not able to track its trajectory exactly due to its dynamic and physical limitations. We introduce a collision-free constraint to the MPC to help the robot avoid obstacles. To ensure a feasible solution, the collision-free constraints are relaxed by adding slack variable delta. By linearizing the dynamic and simplifying the collision-free constraint, the nonlinear MPC is simplified to a linear MPC, which forms a quadratic programming (QP) problem. The nonlinear MPC runs at around 120 Hz and the linear MPC run at around 400 Hz. We present a simulation result of the optimal path found by our method, with 6 obstacles of varying sizes present on the field. This video demonstrates how our robot navigates the field, finding a path to the ball while avoiding static obstacles. We can see the robot slow down and maneuver around obstacles as it approaches them. Video on the left shows how the robot moves to the goal pose along a collision-free path and kicks the ball. The video on the right shows our robot replanning its path to avoid colliding with a human who jumps into its way. Performance of our method was successfully demonstrated at RoboCup 2024. The first video shows in the defensive scenario, Artemis quickly reached the defense position and cleared the ball ahead of the opponent. The second video highlights Artemis's ability to smoothly navigate through a clear path to the desired position and score a goal. In the third clip, despite the ball being close to the goal and under pressure from the opponent robot, Artemis skillfully maneuvered to the target position and scored a goal. We would like to acknowledge our teammates and significant past contributors. Also, we would like to thank all donors for making this work possible.